analysis of CO2 mixing in the human upper airway during asymmetric high flow therapy. So first, just some quick background. We'll be looking at two different cannula geometries for high flow nasal cannula or HFNC therapy. So this is a modality in which respiratory therapy is delivered via a nasal cannula. So this is heated and humidified oxygen specifically. And we're attempting to minimize CO2 rebreathing in the domain here. So just a quick overview of the domain. We have the upper airway up here with two different nasal cannula geometries. It looks like can't really see the laser pointer on here, but we have two different cannula geometries. One is more of a standard dual prong geometry, and the other is a single prong. We also have these mouth open ellipses, so we tested different mouth opening settings, and we wanted to be able to test this without remeshing the domain, because we know that in unstructured meshing procedure like we're using here can induce some unexpected variations if we have to remesh every time we want to change the mouth opening. So rather than remeshing, prior to meshing, we split an interface just behind the patient teeth into a variety of surfaces here, and each of these ellipses is related to a different percentage of the surface area of this total interface. So if we wanted the mouth to be 5% open, for example, we would set the smallest ellipse in the center to an internal face where it would be invisible to the flow, then the rest of them would be walls. So this was kind of our procedure for changing the mouth opening rather than changing the actual domain being simulated. Now, a quick overview of the boundary conditions. All right, here we go. So we have the airway inlet. Inlet is in quotes because it functions as both an inlet or an outlet depending on where we are in the breath cycle. That's the base of the trachea here. So it's a temporally varying velocity boundary in which volume flow rate and species concentrations are being set at each time step. So the volume flow rate is being set to follow a realistic breathing curve that we collected using an ASL 5000 breathing simulator. We also use that same apparatus and a 3D printed airway for our validation study, but we're not really gonna go over that much in the presentation today, but if you guys have questions, I'd be happy to answer those at the end. And then we also track species concentrations during the inspiratory phase. So as the model is inhaling, flow is gonna be leaving out the airway inlet. And as the flow is leaving, we're tracking the total volume during inspiration of oxygen, nitrogen, and CO2 that's leaving the domain. And then prior to the initiation of the expiratory phase, we take those kind of the total volumes that were inspired and we set the species concentration for the subsequent expiratory phase. There's also a surrogate of cellular respiration in which some of the oxygen is converted to CO2 prior to the start of the expiratory phase. The cannula inlet is a steady input of 100% oxygen, and the environment outlet here, which is covering the patient face now, is a pressure outlet with a species feedback of 0.21 mole fraction oxygen. So basically this is just providing ambient room air. Now we're gonna see some contours throughout this presentation, so I wanted to provide you guys an example of the setup. So all of them were collected from profile views, and most of them include the patient facing the right side of the screen, which is what you see here. And they were also collected on multiple planes to deliver a more complete view of the flow in the upper airway. So now if we increase the domain transparency and impose a contour on here, this is an example of what you're gonna see for these contours. So this is a contour of mass fraction CO2, where red is high CO2 and blue is low. And if we just kind of imagine the airway that was up here, this is an outline of the patient face. We have the cannula geometry here, the mouth, and then this is the upper portion of the airway, oral cavity, and then down into the trachea. Now, just a quick summary of some of our previous work. Previously we were looking at all dual prong cannula geometries at different mouth open percentages. So the top row is dual 100, so that's a dual prong geometry with 100% mouth opening. Bottom row is dual 20, so we have a 20% mouth opening there. And what you're seeing here is contours collected at 3 important timestamps. So we have peak exhale, the moment in the breath cycle at which the patient was exhaling with the maximum volume flow rate, expiratory volume flow rate. Peak CO2 is in the middle, so this was the moment in the breath cycle at which the most CO2 was entrained in the airway, and that's not counting the CO2 kind of escaping out into the environment region, so it's just the CO2 in the actual airway. And then end exhale is the moment just before the inspiratory phase starts. And we care a lot about that timestamp because that's kind of giving us a snapshot of how much CO2 is available for rebreathing. So we want to minimize the amount of CO2 at end exhale. Now, just to point out a couple important distinctions between dual 100 and dual 20. As we're closing the patient mouth, you can see higher CO2 entrainment at peak exhale and peak CO2, where this red CO2-rich expiratory air is kind of breaching the upper airway, where with 100% mouth open, that's just all being kind of redirected, evacuating out the open mouth. So for the 20%, we also see this high CO2 front, where we can see kind of the momentum battle between the therapy flow being injected and then the expiratory flow that wants to make its way out of the airway, but it's being restricted by that partially closed mouth. And then there's kind of this front that develops in the upper portions of those nasal passageways. And then by end exhale, for dual 20, the therapy mostly recovers, but we still see some additional latent CO2 that would be available for rebreathing on the subsequent inspiratory phase. Now, just to kind of cover the proposed mechanism for why we were interested in the single prong cannula, the hypothesis is essentially that we're leaving one of the nasal passageways open in difficult to flush scenarios where the patient mouth might be closed or mostly closed, and this would allow the stale kind of expiratory flow to evacuate out that open nasal passageway. So some animations are going to play here. What you're going to see are path lines colored by mass fraction CO2, and they're released from the cannula inlet. So this is indicative of kind of the path of therapy flow in the airway. So for dual prong on the left, we'll see the therapy flow enter the airway and then kind of quickly be turned back around as it's kind of meeting that expiratory flow and it can't reach the back portions of the airway. Now for the single prong, we can see it's being injected in the left nasal passageway, making its way back to the nasopharynx, mixing with expiratory flow, and then being redirected out the right nasal passageway. And the color of these path lines are changing, or more like kind of path streaks. They're like cut off so that you can see the actual traversal here. They're changing as they're mixing with expiratory flow, and the mass fraction CO2 is increasing as it's evacuating some of that CO2 out. So now what we have here is delta CO2 versus time for 5 different therapy flow rates. So delta CO2 is essentially just the instantaneous CO2 remaining in the airway for a dual prong geometry minus the instantaneous CO2 remaining in the airway for a single prong. So what that means is a delta CO2 greater than 0 means there's more CO2 entrained in the airway using the dual prong than the single prong. And end exhale, which I mentioned before is in kind of an important timestamp for us, is at a time of 2.5 seconds. That's the right-hand side of the plot. Now, there are a couple interesting phenomena here. One is you can see at end exhale, as we are increasing the therapy flow rate, we're decreasing the delta CO2 value. So they're all above 0, which means the single prong is entraining less CO2 than the dual prong geometry. But the magnitude of that value above 0 is changing as we're changing the therapy flow. So really we're just seeing that the single prong geometry has more benefits at lower flow rates. Now another interesting phenomenon is kind of the transient characteristics of the 12 liter per minute curve. We can see that for 21 through 45 liters per minute, the overall shape of the curves are very similar, whereas when we change to 12 liter per minute, we can see that it kind of crosses over some of those signals. It has a much different shape than the higher flow rates. So this is something that we think might warrant some future investigation, kind of filling in the gaps between 12 and 21 liters per minute and seeing if we could kind of find out more about that changing transient characteristic for that 12 liter per minute curve. Now moving on to some more CO2 contours. Now, as opposed to different mouth openings, we have the different cannula geometries here. So these are both for a 20% mouth opening, and we have dual prong on the top and single prong on the bottom. These are the same contours that we saw for the dual 20 before. Now for the single prong, these contours were collected in the right nasal passageway. So this is the open nasal passageway available for CO2 evacuation. Now we can see that during peak exhale and peak CO2, we have high concentrations of CO2 in the nasal passageway, and that's what we'd expect. That's what we want, because we want that stale expiratory flow to be moving through this open passageway. But then by end exhale, we could see very little, near zero or zero concentrations of CO2 in the upper airway for single prong, and really the only CO2 remaining is in the oral cavity, where that restriction of the partially closed mouth is creating some latent CO2 here, and then also down kind of below this the conjunction of the upper airway, the nasal passageways, and the oral cavity, where below that it's very difficult for the therapy to actually reach down there and flush out that region. Now our primary metric of effectiveness was the mass CO2 inhaled. So we calculated that for each breath cycle, and we time averaged multiple breath cycles after we had reached quasi-steady state to get a value for each therapy flow rate and each cannula geometry. So this is average CO2 inhalation versus therapy flow setting for each of those. And the single prong cannula consistently resulted in lower CO2 inhalation than the dual prong cannula. But once again, similar to the delta CO2 plot, the distinction between those two curves varies based on the therapy flow. Where at higher therapy flow rates, it's very similar performance, but as we reduce the therapy flow, then we really see the two cannula geometries separate. Now, all the previous analysis was conducted at a 20% mouth opening, but we wanted to see what would happen for each cannula geometry if we fully closed the patient mouth. And the dual prong cannula showed a greater drop in effectiveness when the mouth was closed. So for the single prong, we went from 2.06 milligrams of CO2 inhaled to 2.75, and for the dual prong, we went from 2.19 to 6.95 milligrams inhaled. So a much more significant performance drop-off for the dual prong. Now the CO2 information was kind of our primary analysis, but we also wanted to look at some secondary metrics. So we looked at strain rate in some important regions. We have contours to the right of the right and left nares for the dual prong up top and the single prong down below. And we circled some important regions here where for the dual prong, we have a relatively lower strain rate, kind of back in the nasopharynx, where this is a region where we would expect higher mixing for the single prong geometry as the therapy flow is kind of moving from the left nasal passageway and then mixing with that expiratory flow in this region, and then moving back out the right nasal passageway. Now some other regions where we noticed some distinction was right around the cannula geometry, or really like the exits to the nares, where for the dual prong geometry, we could see some high mixing right outside the cannula geometry, where we kind of noticed in those animations that the therapy flow was trying to make its way into the nasal passageways and then getting kicked back out. So we see some higher strain rates here, whereas for the single prong, right next to the cannula geometry, we can see much lower strain rates, as we would expect more of that therapy flow to be unimpeded going up into the left nasal passageway, whereas the right nares that's open, we'd expect higher strain rates here as that flow is kind of escaping the airway unimpeded as well. So we also released some path lines from the airway inlet colored by residence time.
1 minute.
Thank you very much. So really what these are showing is just how quickly the flow is able to escape the upper airway. So as you're seeing more red in the dual prong geometry up top, you can see that the CO2 rich expiratory flow is really just getting caught in those upper portions of the airway, as we've been discussing. And then for the single prong down low, we don't see as high residence times, and all the path lines, when you can see on the front view, all the path lines for the expiratory flow are leaving that open right nares. In conclusion, we developed CFD models to investigate the effect of asymmetrical flow on CO2 flush for high flow therapy delivery. And at an intermediate mouth opening, the single prong cannula consistently resulted in lower CO2 inhalation than the dual prong cannula. And when the mouth was completely closed, the distinction between those was actually increased, so that the single prong performed comparatively better than the dual prong at a closed mouth as well. And the single prong cannula also resulted in lower residence times than the dual prong, so essentially this is just saying that expiratory flow is more easily and more quickly able to evacuate the airway for the single prong cannula than the dual prong. Thank you very much, and are there any questions?